a non-singular model, inflationary model, which is, well, there are many, but in particular there's the one which we've been working on, which we call the emergent universe. And it starts off at Einstein static, and it goes to inflation, and then it goes to in a standard hot Big Bang. It has a very physical potential, and I think that Jeff will be talking about it later in one of the later talks at this meeting, so I'm not going to say any more about it, except to emphasize it is completely non-singular. It's totally regular. It's got a very nice physical potential. The only thing which the criticism which you can make about it, it is very special, and it's very special because it comes out of that Einstein static point we saw in that last phase plane. It requires a very, very careful balancing of initial conditions in order to start off from that initial state. And initially, the whole point about inflation was it was supposed to be combating special initial conditions, combating that kind of fine-tuning. Now, there's 2 points I want to make about this. The first point is that whether or not the real universe is fine-tuned is an open question. It is not a question which physics is able to settle. The initial conditions for the universe may have been set up in a fine-tuned way, or they may not. They may have been set up in a generic way, and we have no physical theory which can tell us which is what actually happened for the real universe. So fine-tuning, the fine-tuned, very special initial conditions nowadays is not philosophically fashionable. Some 20, 40 years ago it was philosophically fashionable, but the point is it is a philosophical question, not a physics question, whether the universe is fine-tuned or generic. The second point I want to make is something very strange is happening in the inflationary community. There is a group of people working on inflation who are trying to claim that inflation says that K is not exactly, that in fact the universes are exactly spatially homogeneous, and you will find a sub-literature of the inflationary literature which says this. This is very odd indeed, because inflation was supposed initially to be combating that kind of fine-tuning. That's exactly what inflation was about. And this is exactly the same degree of fine-tuning as we are getting in this non-singular inflationary model of ours. Because if you remember in that phase diagram, you are choosing that one very special model in which you're balanced to an infinite number of decimal places. Not a finite number, an infinite number of decimal places in order to get K is not exactly. That is an extreme degree of fine-tuning. And there is this strange part of the inflationary literature suggesting that this is what inflation says. I want to tell you inflation does not say that. Inflation has nothing to say about the sign of K. You can get inflationary models with +1, with 0, and with -1. And this model is infinitely improbable within the family of inflationary universes, and it should be treated as such. You can, if you want, to say that that is what you've got, but then you must say, I am choosing from all possible inflationary models an incredibly fine-tuned model as the one which I'm supporting, and there is no fundamental theory which tells you that this will in fact be the initial conditions for the start of that inflationary model. Okay, now, that ends that section, and we can get on. Oh, sorry. You've now got these notes, and I have some comments there on pages, what is page 120 and 121, about how these models relate to observations. And I'm not going to say much more about this, except to say there is nowadays a concordance model. And in this concordance model, the density of the lambda term, the effective density, is about 0.7. The density of baryons is about 0.02. The density of dark matter is about 0.3. And the total density is approximately 1. I emphasize approximately. And this concordance model, there is a great deal of evidence for, and I will be talking about it this afternoon in the public lecture, so I'm not going to say any more about that model at this particular time. There is a lot of evidence for it, which I will be briefly covering this afternoon. So, what I'm now going to go on to is, in these notes, section 7, the question of observations. And of course, cosmology means nothing without observations. So to look at the observations, you start off with our metric tensor, which we've been looking at before, minus dt squared plus a squared of t into dr squared plus f squared of r into d theta squared plus sine squared theta d phi squared. And you ask yourself, how do observations work in cosmology? Well, they work like in all relativity. We observe down the past null cone, down past null geodesics. A null geodesic will be a null vector, and it will be a geodesic. Now, in the Robertson-Walker models, because of their symmetry, we only need to look at radial null geodesics through the origin. Now, at first that might look an enormous restriction, only radial through the origin, but that is a generic geodesic because of the spatial homogeneity and the isotropy in these universe models. So you can put d s squared as naught, you can put d theta as naught, and you can put d phi as naught, and the basic equation for null geodesic there is naught from d s squared is minus dt squared plus a squared of t dr squared, because you put the d theta and the d phi to 0. And so you can solve that to say dr is equal to dt over a of t with a plus or minus. The plus or minus is the incoming or the outgoing null geodesics. And then you can integrate that. And that's the basic equation for null geodesics in a Robertson-Walker model. It immediately follows from the metric tensor of these space-times. Now, from that, you can deduce what you basically need, and I'm not going to do sort of a whole in-depth calculation of everything because they are in those notes. I want to just point out what the basic features are, and the first feature is redshift. And you've all heard about redshift, and that is 1 plus z is delta lambda, the change in wavelength over the wavelength emitted. And what you need for redshift is from here, in a couple of lines, what you do is you look at light emitted at an initial time, t, and then at a slightly later time, t plus delta t, te, t plus delta t emitted. These are received up here at TO and TO plus delta TO, and what you calculate is delta TO as a function of delta TE, and that comes immediately from this equation up here, and the details are, well, it comes immediately out of that. That is, as it were, a simple exercise out of that, and the result is the one which is very, very well known. It is the scale factor at the time of observation divided by the scale factor at the time of emission. And this is the first very, very basic and important result in Robertson-Walker cosmologies. Redshifts are a direct measure of the amount of expansion that has taken place in the universe. And I want to just make a basic point about it. This is basically a time dilation effect. Basically, what is happening is that this period here, the period at the time of emission, is measured through this equation here to be slightly different from the interval at the time of observation. To get this result, you apply it to the period of an oscillating waveform, and it gives you the redshift. But this applies to all observations. So, for instance, if you're looking and you're measuring a quasar at a redshift of 4, and you see it varying on a period of some hours, for example, what you must do is you must realize there's a time dilation factor, and in fact you must change them and say it was actually oscillating at a rate which was a factor 5 times different from what you have measured. Everything you are seeing is changed by the factor 1 plus z. The small oscillations of atom that leave to wavelength are different, but also the macroscopic variations in intensity of light of any distant object are also different by exactly the same factor. That's the first point. And the second point is that this is the cosmological redshift. Now, this is the cause of one of the major problems in cosmology, that what we're assuming here is we are assuming that the emitter and the observer are both fundamental observers. They are both moving at exactly the right velocity. The problem is that your observer, your emitter, may be moving at a different velocity because there are random velocities in galaxy clusters. And we are also not moving at exactly the fundamental velocity. We are moving at 300 kilometers a second relative to the fundamental velocity. Now, the observed redshift can be written as 1 plus z Doppler at the emitter, 1 plus z cosmology, 1 plus z Doppler at the source. And there are actually also factors 1 plus z gravitational at the emitter and 1 plus z gravitational at the source. If you put it all together, you can get gravitational redshifts down there plus Doppler redshifts down there. You can get gravitational redshifts up here and Doppler redshifts or blue shifts, depending on the case. And this is why the subject of redshifts is not as simple as you might have thought to begin with. You've got a lovely, beautiful theory in Robertson-Walker models for the cosmological redshift, but you can't observe the cosmological redshift. You observe a redshift, one redshift, and you have to split it up. How much was gravitational at the emitter? How much was Doppler at the emitter? How much was gravitation at the source? The observer. At the source, this should be the observer, and that should be the source. Well, these we can handle. There's basically very small effects there, but one of the questions which has always been relevant, how big a Doppler shift can you get down there, and how big a gravitational redshift can you get down there where the source is? Now, in fact, a lot of theorems have been proved using general relativity that you can't get very great gravitational potential wells for stable sources, and most of the remaining discrepancy is when you look at a photographic plate at what looks like a cluster of galaxies and you measure the individual redshifts, you have to use astrophysical argumentation for each source to decide what is the cosmological part and what is the local Doppler part due to the local motion of those objects down there. And that's one of the reasons that measuring distances in cosmology is difficult, is because these random velocities give you random Doppler shifts, and so your observed redshift has to be broken up on the basis of astrophysical argumentation into the cosmological part and the Doppler part. What that means is you have to assign a cosmological average motion to that cluster, and then the individual galaxies you assign Doppler shifts relative to that average. That cannot be done by any fundamental principle. It has to be done by looking at the cluster and estimating its dynamics. So that's one of the reasons redshifts are not as easy in cosmology as one might have hoped. Okay, the second thing that you get is angles. And we look down at one angle, theta, and we look at another angle, theta plus d theta, an angle. And down there, that corresponds to some length L. And what you have to work out is what is that length L as a function of this angle? Well, what we do is we define something we call the observer area distance. And by definition, L is equal to alpha d, is equal to R0 times alpha. So we define the observer area distance such that the standard relation holds size is proportional to angle. But that just shifts the problem. We now have to go to our metric tensor and work out what is the actual, what is that quantity. So we have to use our Robertson-Walker metric to determine how distances go down there. And I'll just show you the starting step of this. The starting step is you go back to the metric tensor and say, down there, how do we work out from this metric what the distances are? Well, down there, we're going to be looking at a galaxy at an instant of time. So in this case, dt will be 0 because we will be looking instantaneously at the galaxy. And we will assume the galaxy is oriented orthogonal to our light rays, so it will be at constant r. And what you get left with is that part there. And what you can see then, just concentrating on d theta, you see there that ds squared will be to a squared times t f squared of r times d theta squared. That's for the area, and take the square root of that, the length will be a of t f of r times d theta. Now this is the time. When are we evaluating that? Down there at the time of emission. And so that's the basic formula which you compare with this formula here, and you work out that R0 is therefore the scale factor at the time of emission times f of r. How do you then relate that to the actual geometry? Well, firstly, what you see is the spatial curvature comes in a very important way. Because what this is telling you is apparent angles as you move an object down the light cone. So for the same object, move it down the light cone, the apparent angle will be given by the size of the object divided by R0, where R0 is given by that expression. Okay, what happens there is f of r